Seinfeld, which is going to talk about Latin America high energy physics.
Hi. Hello, everyone. So welcome back from the break. So I'm going to talk in 15 minutes. This talk was supposed to be yesterday, but was rescheduled. I'm going to talk in 15 minutes about a huge effort that is being made in the region, a community effort, and this is the high energy cosmology and astroparticle physics in Latin America. So this is a community effort, and I'm speaking on behalf of the LAA HICAP board and the last preparatory group. By the end of this talk, I hope you will be familiar with these acronyms and also with this logo. This is the logo of the Latin American Association for High Energy Cosmology and Astroparticle Physics, and this is the logo of the Latin American Strategy Forum for Research Infrastructure. Okay, how do I go forward? Here. So there are two main community efforts in high energy cosmology and astroparticle physics in Latin America. So I call HICAP these areas. One is the Latin American Symposium in High Energy Physics. This is called SILAFI. The other is the Latin American Strategy Forum for Research Infrastructure, LASFRI. So SILAFI has a long tradition, and it is the premier meeting of the high energy Latin American community. It takes place every 2 years in different countries in Latin America. The 15th edition happened in 2024 in Mexico City, and the 16th edition will be in Bogota this year, and this is the poster, and we invite everyone here interested to go to Bogota. Some of the organizers are here, like Davis Moreno and others are here. Now, the other Latin American effort is the Latin American Strategy Forum for Research Infrastructure. We call it LASFRI. This is a more recent effort. It aims at developing a strategy to strengthen the Latin American scientific collaborations and their impact. This was inspired by the SNOMAS P5 process in the US and the European Strategy in Particle Physics in Europe. This is the logo for LASFRI, and this is the page where you can find all the information. The main goals of this process is to chart the landscape of existing infrastructure and expertise already developed in the region to build consensus and support a strategy-based approach for the participation in and development of large-scale research infrastructure projects in Latin America, to make a call to the Latin American scientific community to establish a strategic scientific forum in order to coordinate Latin American activities in this area, to set up the Latin American scientific roadmap based on actual participation in large-scale research infrastructures, an inherent need for long-term planning and funding in implementing an open call for input from the scientific communities, and to enable a more effective development of the Latin American research groups, facilitating multilateral participation in regional and global research infrastructures, increasing their impact, and to inform ministerial meetings of the development, implementation, and impact of the strategy for HICAP. So the first strategic planning of Latin America was finished in 2021, was based on 39 white papers submitted by the community after a call, and 3 main documents were produced. The Latin American HICAP Physics Briefing Book, the strategy document with some recommendations, and the endorsement letter from the high-level strategy group. All these documents can be found in this link. This is the endorsement by the high-level strategy group of the first update, and they strongly recommended that the HICAP community put in place a robust structure, a mechanism that would allow the community to come together on a periodic basis, ideally about every 5 years, to examine progress and consolidate community input. So, following this recommendation to create a robust structure, the Latin American Association for HICAP was established during the SILAFI 12 in November 2021 as an association for the Latin American research community in the fields of high energy cosmology, astroparticle physics. So the objectives of this organization were declared in the bylaws. The first General Assembly took place during the 14th SILAFI in Ecuador, 2022. The second General Assembly took place in the 15th CILAFA in Mexico, and the third one will take place in the CILAFA in Bogota later this year. The membership for the Latin America Association is just by filling a Google form. Anyone interested in this in HICAP can join, and we have more than 650 members registered. Outside there is a folder with a roll-up with all the information about LAA HICAP. So this is the page of the Latin American Association for High Energy Cosmology and Astroparticle Physics, and again you can find all the information you need in this link. These are the again goals of this association. I'm not read them again. And some highlights of activities of this association was to carry out some mobility programs in Latin America. So we got resources from the CTP network program and also from CLAF. And members of the LAA HICAP were nominated for the preparatory group of the European Strategy in Particle Physics. We submitted regional input to the European Strategy in Particle Physics with information questionnaire. So this was a regional input. Also, there was a nomination of LAA HICAP representatives to C11 and ICFA. We're finishing an update of the Latin American strategy in HICAP in 2026. And also, this association is one of the main reasons why ICHEP is being held in Latin America for the first time in 2026. So now I'm going to talk about the update process of the HICAP strategic planning in Latin America. So what we're doing, so there was a call for new or updated white papers that was issued in November 2023 with a deadline of July 26, 2024. The submitted contributions were presented in a symposium, an open symposium. It was the third last HICAP symposium, and this was specific for the updates of strategic plan. This was held at ICTP SAFER in São Paulo in August 2024 with the participation of the preparatory group, the high-level strategy group, funding agencies, and representatives of similar efforts around the globe. So this is the page of this meeting, of the symposium, and all the slides and videos are available in this website. The invited speakers were many, so Luciano Maiani, who is actually the chair of the high-level strategy group, Galvão, were people from the BID, from several national agencies. IFANG was there remotely also. Christophe Grosjean and Tosh Murayama talked about the P5. Paris Esficas talked about the ESPP. So this is the preparatory group. So we model this as the European strategy. We have a preparatory group and we have a high-level strategy group. We have representatives from different countries in Latin America. Some of them are here in this conference. An updated physics briefing book that was based on the 48 white papers that were submitted. This was concluded in 2025. And you can find this in the archives. We put the first version in the archives in March 2026. And it's a comprehensive book about the physics topics that were presented in these 48 white papers and shows the participation of the Latin American community in many efforts related to HICAP. An update strategy document was drafted based on, again, on the physics briefing book. This was finished recently. The Latin American strategy for HICAP. And this, again, this is a preparatory group. There was a subset of us that were in charge of writing this strategy update. And one of the outcomes of this update is a landscape of participation of countries in Latin America in different experiments. So we just flash and we have 30 seconds to look at these things. So we have this is the kind of landscape that we have. We also have tables, and these are the countries. This is in high energy and nuclear physics. These are the ongoing experiments, and these are the future experiments. These are the countries, and the lines, of course, are the countries which are participating in these different efforts. This is in astroparticle cosmology and gravitation, the same type of thing. You can find everything in the document, but it gives you an idea of the involvement of the community of Latin America in all these experiments in the world. And this is in neutrinos and dark matter. So you can see how the Latin American community is involved in several experiments. So a set of 10 recommendations was made. This is just one of them, just to give an example. You can look at the strategy document. And then this strategy document was sent to the high-level strategy group of LASFRI. And this group, which is composed by, these are the composition of the high-level strategy group. So from Argentina is Teresa Dova, from Brazil is Inácio Bediaga, Chile is Claudio Dib, etc. And it's chaired by Luciano Maiani, and the co-chair is Fernando Quevedo, who is here. So what this high-level strategy group did was to look into the strategy recommendations, and then they made their own comments about that. You can see that this is very recent. This is July, so this month, basically. Yeah. And I'm not going to read through this, but you can see these are some of the recommendations of the high-level strategy group: engagement in future colliders, leveraging artificial intelligence in Latin America, and adapting to regional experimental shifts, which happened between the first strategic planning and the second strategic planning. Basically, Andes, which was the flagship project that was supported by the first strategy planning, and this is now having issues, and as WGO has been highlighted in the strategy document now. So in conclusion, I want to say that the high energy cosmology and astroparticle physics in Latin America has experienced really rapid growth. Between the first and the second, the first strategy plan and the second strategy planning, many things happened, such as Brazil and Chile joining CERN, but many other, as associate members, but many other things have happened. SILAFI has been the forum for discussions of ICHEP in Latin America since 1996, and still is. So this was the first bottom-up strategy planning in ICHEP in Latin America, and this was done in the years of 2019, 2020, and reviewed a rich landscape. The community here created this association, the Latin American Association for High Energy Cosmology and Astroparticle Physics in 2020 to coordinate efforts in the region. Many results were already reached, so we have mobility programs within Latin America, visibility in ICHEP for Latin America with representatives in committees, etc. And what I want to report really here is that the first update of the strategic planning has been concluded. So we plan to send these recommendations out, the whole process, for the C11 for endorsement. That we didn't do last time, but we want to do this. So I really want to say that an engaged ICHEP community in Latin America is being developed and organized. So let's keep the effort going. Thank you very much.
Thanks, Rogério. So we have time for a couple of questions. Yeah.
Good morning. I am Alberto Santoro, and I would like just to make a comment that Leon Lederman, years ago, started a new wave in Latin America. I believe that for Brazil, for example, Leon Lederman and Maiani are the two persons, the two physicists that have a big effort to create in Latin America a new wave for high energy physics. I would like to do a recommendation to contact Monica Bruckmann, who was the leader of an initiative years ago in which I participate, to CERN to try for the first time to create an agreement between CERN and the UNASUR that for the whole Latin America. I believe that we have to talk more about this, but it's just a comment and advice to say let's go in this direction because this is very, very important initiative.
Thank you, Alberto. Just say that we are in contact with CERN and they are participating in this initiative.
Does this work? Okay. So I was interested that in the discussion of your roadmap, then you included nuclear physics, which I know is active in South America, but you did not include it in the title. To what extent is the nuclear physics discussion integrated into your enterprise?
Yeah. So again, thanks for the question, Mont. So this is a community-based effort. So if there are people in this nuclear high energy, let's say nuclear community, people that do JLab, for instance, things like that, if they submitted a white paper showing what they're doing, we're going to, of course, include this. And this is what we're doing. So again, this is a community. This is not us. This is the community. It's not us. I mean, the preparatory group. We have to work with the white papers that are submitted. Thank you.
So we have no more time for questions. So let's thanks Rogério again. So our next speaker is Julieta Grusco, who is going to talk about neutrino mass measurements. Please, Julieta.
Great. Thank you first to the organizers. It's been such a pleasure getting to talk about physics with all of you in such a beautiful place. So I'm going to tell you a bit about neutrino mass and double beta decay. I think it's become clear to all of us that the standard model is annoyingly correct so far. It has very few cracks in it, but we know we have questions we still need to answer. The one exception to this is the BSM physics that we've seen in the laboratory, which is neutrino mass. This is arguably the only BSM particle physics we've seen at 5 sigma in multiple experiments. And now the question remains, is this BSM that doesn't help us solve any other problems, or is it BSM that helps us get access to what's actually going on here beyond the standard model? And so, if we discover neutrinoless double beta decay, that would help us explain neutrino masses while giving us access to seeing exactly what kind of beyond the standard model physics we have. So really here we're talking about two questions in this talk. One is what is the neutrino mass? And the other is why are neutrinos so massive? Or why do they have mass at all, right? Or why do they have mass that's not zero? But also they're very small in mass, right? This is not naturally occurring within our standard model or even within minimal extensions of it. So yesterday and right after me, you've heard a bit about neutrino masses in the history of our universe. So today, I'm going to focus on what neutrino masses tell us in the laboratory. So really, there's two options for giving the neutrino a mass. Andre told us more about this earlier today, so I'll keep it brief. If we add a Dirac mass term, we need to add some non-interacting fields to our model. On the other hand, if we add a Majorana mass term, this could be generated by new physics anywhere from the TeV to the gut scale. You could have both types of terms. Any non-zero Majorana mass term makes the neutrino a Majorana fermion in common parlance. So neutrino masses can be generated by a range of models that lead to one or both of these terms. So the model that experimentalists like to talk about is what I would call sort of the minimal model of Majorana neutrinos, which is a type 1 seesaw mechanism. If we just add a Majorana and a Dirac term and make the Majorana term at least a bit heavy, you end up with 2 light neutrinos and 2 heavy neutrinos. So the light neutrinos are our everyday neutrinos that we interact with, and the 2 heavy neutrinos get stashed away somewhere at high energy, where the scale of them depends on the Majorana mass scale. So part of the reason people like this model is that if you put that Majorana mass term at the gut scale and the Dirac mass term at the electroweak scale, you naturally get out a very light neutrino that looks like the neutrino we see with the new physics stashed away where you expect new physics to occur anyway. There are lots of other mechanisms that would generate light neutrino masses. Some also generate baryon asymmetry or dark matter candidates. Some can be produced at colliders and generate new particles of order 1 to 10 TeV. The real motivation behind a lot of this work is that many Majorana neutrino models also satisfy the Sakharov conditions that are required to generate baryon number asymmetry. So we're really trying to solve one problem with another here. Okay, so if we want to understand the neutrino, we have to know its mass. And the work I'm going to tell you about here is not my own. It comes from contributions from these experiments, so thank you to those folks for providing materials. All of these neutrino mass laboratory experiments work via the same concept, which is they measure the endpoint of a beta spectrum of some sort. You're directly measuring how the phase space modifies the endpoint of this spectrum. And so you're sensitive to how the neutrino couples to the electron, and you get the maximum distortion at the endpoint. So in the beta decay method, you're measuring some sort of beta decay where the neutrino mass information is encoded in this electron's kinetic energy. Tritium here is the leading method. That's because tritium has both a low energy endpoint, which gives you more events near that endpoint, and because it's a super allowed decay, meaning we have quite a nice simple spectral shape to calculate. The other method that's ongoing is the electron capture method. Here, the neutrino escapes, and the neutrino mass information is encoded in the de-excitation of that nucleus. This has an even lower Q value, meaning you get even more events at the endpoint by about an order of magnitude. But as you can see here, the spectral shape is a bit more complicated because you can capture electrons from many shells. And so you need more precise spectral modeling, which has advanced a lot in the last few years. So this field has a long history. Even before we had detected the neutrino, we had already started setting limits on its mass, and even before oscillations told us conclusively that it did have mass, we were also doing these studies. But the experiments I'm going to tell you about are those that are going on right now. The leading experiment, Katrin, and some R&D efforts going on in other projects. Okay, so Katrin uses a technique called a MAC-E filter, which is magnetic adiabatic collimation with an electrostatic filter. What that means is that they have a very high activity of tritium in a windowless source, meaning it's just a volume of gas that's decaying away, and you use differential pumping to bring down the rate of electrons from the very high rate that you have here and take just the highest energy ones into your spectrum. So you guide the electrons with magnets into this adiabatic collimation region where you get them all pointing the same direction, and then you apply an electrostatic filter and count just the electrons that make it over that potential barrier. So this is an integral measurement. You have to scan through energies and count. At the end, you do a 4-parameter analytic fit. You have floating here the amplitude, the background, the endpoint, and of course, your parameter of interest, m beta squared. So Katrin has released data from its first 5 campaigns. You can see here that as time's gone on, they've gotten lower and lower backgrounds and more precision on the model. With these 5 campaigns, they've set a limit of 0.45 EV for M beta. But they're not done. Katrin has a lot more data on disk, and we expect new results in about 2027. The statistics tell you that you should be able to reach about less than 0.28 EV of sensitivity. They're working on pushing down the systematics to make sure that that's the case. In the meantime, they're also undergoing an upgrade to be able to do a KeV scale sterile neutrino search and doing a lot of R&D with quantum measurement techniques, electron tagging, and atomic tritium source development to be able to make an upgraded version of this experiment. At the same time, there's a new player in the game, which is cyclotron radiative emission spectroscopy, or CRESS. So this is the technique pioneered by Project 8. The idea here is that the electrons undergo free cyclotron oscillations in a magnetic field and emit microwave radiation. You pick up that radiation with an antenna, and you can get an extremely sensitive measure of energy. So what you're seeing here is an electron. It's radiatively losing energy and undergoing gas scatters, and you can see just how precisely you can measure that frequency. So this gives you an ability to do a large volume measurement of many atoms at once to very high precision. So Project 8 is pursuing a 4-phase strategy to reach the bottom of the inverted ordering allowed region. They've completed the first 2 phases, and that gave them the first tritium spectrum measured with CRESS and the first neutrino mass limit from CRESS. The next stage is to move to RF cavity search and to demonstrate this move from molecular tritium, which has broadening from final states, to atomic tritium. So the phase 3 goal here is to reach down to 0.3 to 0.7 EV, and the ultimate goal for phase 4 is another order of magnitude improvement. There's also R&D going on with quantum sensors. So the experiments doing this are ECHO and Holmes, both of which use calorimetry. You embed this holmium isotope in a microcalorimeter and read it out with some sort of quantum sensor. You need to make these calorimeters slow because pileup is a major concern here since they don't read out very quickly. So you need multiplexed arrays, and this is a place where we're really taking advantage of improvements in quantum computing. Holmes is doing this with a transition edge sensor technique, ECHO with a metallic magnetic calorimeter, and both are seeking to push demonstrations of the technique down to the EV scale. Okay, so now let's pivot to my dearest love, which is searching for neutrinoless double beta decay. So this is why is the neutrino massive? Now, to tell you about neutrinoless double beta decay, I have to briefly introduce you to the neutrino full version, which is that in certain nuclei, single beta decay is disallowed, and instead we get out a double beta decay. This is a second order weak process, so really long half-lives here, about 10 to the 20 years. Now, if the neutrinos have a non-zero Majorana mass term, instead of emitting 2 antineutrinos, you can exchange a virtual neutrino between these vertices. In that case, lepton number conservation is violated by 2 units. And no matter what the model is, no matter what we've packed in to this little mass cross there, you have some really exciting implications. One is lepton number violation, and the other is that neutrinos have a Majorana mass. So that's the BSM physics we're looking for. Now, in this crowd, I don't need to explain missing energy to anyone. Our 2 neutrino double beta decay has missing energy. The neutrinoless version creates only charged particles and does not. So that's the signature we search for. We see this huge spectrum from the 2 neutrino double beta decay, relatively huge. It's a 10 to the 20-year half-life, of course. But what we're looking for is this little peak right at the end point that comes from the neutrinoless version. You can also use topology information if you can understand what's going on with these betas to help tag it. So if you write down this diagram, you can translate it to an expected rate. And of course, you couple in all of the neutrino physics because you've got this sum over the PM&S matrix. And you introduce 2 unknown phases. And that creates this plot you may have seen before, where you have the lightest neutrino mass on the x-axis and this effective Majorana mass on the y. And you can see that the ordering makes a difference, but the breadth of these bands comes mostly from those unknown mixing angles, unknown phase angles. So our goal for our coming generation experiments is to explore down to the bottom of this IO band. Now, of course, we've been hearing more and more that we might be living in a normal ordering universe. So I'm going to tell you here, these are not separate ideas, right? When you explore the IO band, you also explore the NO region. And the parameter space we'd cover here is probably about half of the NO parameter space with this goal. So it's the first step. It wouldn't take us all the way through that parameter space, but it's quite important to do. So most experiments use the same idea. They go deep underground, very clean, make the experiment, the detectors themselves, out of the isotope of interest. That gives you very high efficiency for making this measurement. There's 2 basic ideas. One is to use granular detectors, lots of small detectors that tend to have better than % level energy resolution and allow for staging, or monolithic detectors where you have a large volume that's more scalable but tends to have lower energy resolution. And of course, we all try to use techniques for background suppression like event topology, particle ID, and many other things. So this is a huge landscape of experiments. I obviously can't cover all of them. I'm going to do my best to tell you what's coming next. We've had a suite of completed experiments, running and under construction experiments, some of which I'll talk about, and proposed experiments looking to the future. As you move to the bottom right here, we're getting very large exposures with very low backgrounds, and that's what you need to discover neutrinoless double beta decay. So here's the current state of the field. We've got the most stringent limits from a few isotopes here, and you can see that we're all reaching about the 10 to the 25 to 10 to the 26-year half-life level. The reason you see a light gray band here is that there's a lot of uncertainty in the nuclear physics you need to translate to M beta beta. And so depending on whether you take the most optimistic or pessimistic limits here, we're either starting to explore well into the inverted ordering band, or we haven't even reached it yet. Okay, so this is the experiment I work on. So this is Legend 200. We use germanium detectors enriched in germanium-76 and operated in a bath of liquid argon. That gives us a lot of really powerful ways to reduce backgrounds. With our signal is a single site event within one detector. And anything that has multiple scatters, whether within one detector, multiple detectors, or a germanium detector in argon, is a background, and that's how we reject it. So we just released our first result based on the first year's worth of data taking. Here's what the spectrum looks like. And what you're seeing here is before the cuts in white, after liquid argon cuts in gray, and after all cuts in red. And you can see here almost a pure 2-neutrino double beta decay spectrum, and our endpoint is where we're looking for our signal. Here's a zoom in of what that looks like. This is a background of 5 times 10 to the minus 4 counts per keV kilogram year. That means that in the ROI, we expect 0 or 1 count of background. Based on that, we can set a limit. And this is what it looks like. So combining with the previous generation of germanium experiments, we end up just under 2 times 10 to the 26 years. We're still running. Our next data unblinding is planned for our 200 kilogram year benchmark, which will happen early next year. You should expect other new results coming very soon from Legend. In the meantime, we're also working on the design and starting construction activities for Legend 1000. This makes a suite of improvements to Legend 200, including switching to underground argon. And we're in our final design reviews this year with construction at LNGS starting in the next year. So with this experiment, we'll fully explore that IO band going up to 10 to the 28-year half-lives. The other neighbor experiment at LNGS is Core, followed by the Qubit experiment. This Core is a ton-scale bolometer experiment using tellurium dioxide running at millikelvin temperatures. They've accumulated a huge amount of data. Their most recent result is based on 2 ton years, and it's 3 times 10 to the 25-year half-life. For the next stage, they're planning to move from a phonon-only signal to adding light readout. And that lets you do particle identification or type of interaction identification. To do that, they have to switch to a new isotope. It's a lithium molybdate crystal, and that will let them span that inverted ordering region. So they're planning a stage deployment strategy. In the coming years, they're planning to take data with 1/3 of the crystals. That gives them time to make the remaining detectors. And then sometime in 2034 or so, they would move to the full array. Beyond Qubit, they'd need a bigger cryostat, but that would let you start reaching into this normal or purely normal ordering regime. So that's quite exciting. Okay, CamLAN-Xend is the other big player on the block. They finished out their CamLAN-Xend 800 run with the most stringent limits, half-life limits of any experiment at almost 4 times 10 to the 26 years. This is enriched xenon dissolved in liquid scintillator within this inner balloon, read out with PMTs. Now they are under construction. They are building out CamLAN-2Xen, which is putting in a suite of improvements, basically to focus on improving this energy resolution by a factor of 2. With that, they'll be able to reach up to the 10 to the 27-year half-life level. You already heard about SNOW, so I'll just keep it to the double beta decay program. The tellurium loading plan is now expected to start in September of 2027 with a 0.5% loading, which would give them this 10 to the 26-year half-life. But they think they can also get a bit more out by loading more tellurium in the future. Something very exciting, we saw some new results at this meeting from Next 100. This is a totally different technique using a high-pressure xenon gas TPC. What's nice about this is it gives you a pretty good energy resolution and this very distinctive beta track signature. These are signal-like events. They call it spaghetti and meatballs. And these are our background-like events with only one Bragg peak from the beta. They're now running Next 100 with a goal primarily to show this very low background level. And reach a 10 to the 25-year half-life. And they have an extensive upgrade plan, both to reduce backgrounds in the existing experiment and to deploy larger and more sensitive versions of the next detector. The other sort of tracking-focused detector that we should see results from soon is Super NEMO. So this is more like a collider experiment. You have source foils, but they're interleaved with particle trackers and segmented calorimeters. That gives you these very nice, clean beta signals. Looks more like a collider event display, except with extremely low event rates. So an experiment like this could be particularly useful for probing the mechanism behind neutrinoless double beta decay. You can look at the opening angle between the betas or the energy of each of the particles, and those encode really interesting information. So they're currently taking data at Modane, and we expect some results hopefully very soon. So you may wonder what comes next. Well, there's a lot of other experiments underway. They're doing R&D for new techniques. So some of the ones I didn't have a chance to talk about here are candles with calcium-based detectors, or Selena with selenium-based tracking detectors. But if we make a discovery at the ton scale or before, our next step would be to measure in more isotopes or to construct something that can tell us about the opening angles and those other kinematic variables associated with the neutrinos. If not, our next generation experiments are targeting around 10 millieV or smaller. No one really has the golden bullet yet for hitting the 1 millieV level, but there's a lot of ideas and a really rich R&D program for looking at the possible techniques to do this. So some examples I've shown here. This is the Theia Neutrino Observatory concept. This is a proposal for the module of opportunity for Dune that would also be able to do double beta decay. And this is a display of barium tagging for the future next upgrade detector. So I hope you've been convinced that neutrino mass is BSM physics, but we still haven't explained it. So if it's interesting BSM, it could really be a hint of what's going on at the gut scale, so at the very heaviest, highest energy physics. Neutrino mass measurements have reached a fraction of an EV with a plan to go an order of magnitude further in sensitivity. And our searches for neutrinoless double beta decay are starting to probe this inverted ordering region. So we expect searches to reach further into the IO band and even cover it in the coming years. And we're really starting to explore very interesting parameter space, and we're thinking about how to go further. Thanks for your time and attention.
Thank you, Julieta. We have time for questions.
Okay, so, sorry. So just a comment that you mentioned this exciting possibility of having, exploring the gut scale physics due to the typical type 1 seesaw mechanism. I only want to mention that if you had such a scheme, you would have physical corrections to a Higgs mass parameter for the gut scale.
Yeah.
So I guess you will need supersymmetry.
I think the model where you have literally nothing until the gut scale, I believe, is not super well motivated. But yeah, it would tell you some hint of what's going on at the high scales that we can't access directly.
Okay, very good. Just a comment. And the other is that we are unfortunate, right? In the M beta beta in the normal ordering is very small. Right?
It doesn't have to be that small. So let me. There's been several of these analyses looking at trying to parameterize how much parameter space sits at different values of M beta beta. People get very discouraged by this picture. This funnel looks gigantic. But of course, this requires sort of perfect cancellation of your phases. So if you have a model that forces us into this funnel, sure, that's bad luck. But if you parameterize it as a random phase angle or two random phase angles, you get a lot of parameter space piled up near this top edge, where we actually could access it experimentally. So it's not quite as bleak as it looks.
Okay, very good, thank you.
And of course, measuring the neutrino mass could tell us whether this funnel is even allowed, right?
So here, you didn't mention the Juno experiment, which can be upgraded for double beta decay. Sensitivity can
absolutely
reach less than 10 millieVs. So,
So there's a whole landscape of experiments that have double beta decay as part of their future plan. I did not mention them. I tried to give you a picture of what's coming in the next couple of years. The other thing I didn't mention is the sensitivity of the liquid argon or liquid xenon observatories. So you see that LZ already is playing in a similar regime to some of these existing experiments I told you about. If LZ were to move to enriched xenon, they would already be quite competitive. And this is, at the time this was made, it was called Darwin, but now XLZD as well. So there's lots of multi-physics programs that can include neutrinoless double beta decay. Yeah.
Okay, well, thank you very much for your very interesting presentation. So it is known that the neutrinos double beta decay activity is critically dependent on the nuclear matrix elements calculations.
Yeah.
What can you say about the progress in
Yeah.
this field for the next stage experiment?
Sure, yeah. Let me briefly, I cut that thinking this is a high energy audience. They won't want to hear about NMEs. But yeah, so all of these dots that you see here are different nuclear matrix elements from different techniques. These are all sort of our effective kind of traditional nuclear physics techniques of modeling with some effective model. There's also now ab initio calculations that help reduce the uncertainties or at least control the uncertainties available for some of the isotopes. And so this first legend result, I can point you to it because we're the first ones to actually use one of those ab initio models to set limits. So we've had a lot of progress from the theory community on this, and I think there's going to be a lot more in the next few years.
Okay, so let's thank Julieta again for this great overview. Okay, our next speaker is Yvonne Wong, which is going to talk about astrophysical and cosmological neutrinos.
Right, okay, so no need to clap. So I've been tasked with telling you about astrophysical and cosmological neutrinos. So I'm going to begin with this so-called grand unified neutrino spectrum, which basically depicts all the man-made and natural sources of neutrinos that we are aware of. Now, there are many of these neutrinos depicted in this plot that are actually astrophysical in origin, but I think by convention, when we talk about astrophysical and cosmological neutrinos, we are primarily referring to three sources. We have the C nu B, we have the C nu B on this side, the cosmic neutrino background from the Big Bang. We have the diffuse supernova neutrino background from, well, supernova, and also the ultra-high energy neutrinos. The ultra-high energy neutrinos were already covered in a talk yesterday, which is why I didn't circle it, because I'm not going to talk about it. And in this talk, I'll be just talking about these two backgrounds. Now, at this point, I have to confess, even though I'm a huge fan of supernova neutrinos, this is actually not my area of expertise. So the bulk of the talk will, in fact, be on the cosmic neutrino background. Right, but nonetheless, let's begin with the diffuse supernova neutrino background. Now, the reason why I'm talking about it is that Superchemical Kane actually made an announcement at the Neutrino 2026 conference back in June, so a little over a month ago, that they have now a 2.6 sigma indication, their word, not mine, of the DSNB. And that's coming from 5,000 days of data. Now, for those of you who are not familiar with the diffuse supernova neutrino background, it's basically a cumulative background of neutrinos that have been emitted from all core collapse supernovae in cosmic history. Okay? Now, I'm particular about the core collapse supernova because even though all supernovae emit some neutrinos, it's only the core collapse ones that emit neutrinos in large quantities that make them observable. And in fact, neutrinos carry away about 99% of the energy released in a gravitational collapse, okay, which is the core collapse supernova. These neutrinos are essentially thermal because the core of the supernova heats up to MeV energy, so you expect them to be tens of MeV in energy. And these neutrinos stream out of the core over 10 seconds or so, and they're responsible for reviving the shock wave of the supernova that will eventually blow out the mantle of the star. And also, they're responsible for cooling of the proton-neutron star. This picture, this basic picture here of these neutrinos and emission has been confirmed by the 20 neutrino events that were observed in 1987 from supernova 1987A. Now, for the diffuse background, essentially, when we compute from the theory side what this DSMB flux should be, essentially what we're doing is a line-of-sight integral that contains several elements. So you have the part that is responsible for redshift, because we're integrating over cosmic history all the way back in time. So redshifting matters from the expansion of the universe. There is, of course, a dependence on how often supernovae happen at each redshift. Okay? And here, this is actually quite a bit of uncertainty because it depends on a range of things like star formation rate, black hole formation rate, etc. And then, of course, last but not least, you also have to put in a neutrino spectrum per supernova that goes off. And so people have been investigating this for decades, and here's like a big long list of DSMB models that have been published. Okay? So varying quite a lot in the magnitude, but the normalization of the flux, but nonetheless, you can see that you have this kind of decreasing spectrum. So going back to the super K result in this 2.6 indication, so what they essentially did was to take 3 models from that long list of models that I just showed you before, and they adopted the spectrum of each model, and then they performed the fit while varying the normalization. Okay, so the normalization was floated, and there's another 30 or so background and nuisance parameters describing various backgrounds, mostly from atmospheric neutrinos. And as you can see over here in this table, no matter which spectrum that they actually adopted, the significance of the best fit is about 2.6, 2.7 sigma away from the null hypothesis. Okay, so this is a very nice result, if you ask me. Right, okay, so moving now on to the cosmic neutrino background, okay? So these are neutrinos from the Big Bang, so produced 1 second after the Big Bang when the temperature of the universe was of order 1 MeV, okay? And these neutrinos come about because they decouple from the QED plasma, or the cosmic plasma, whatever you want to call it. Now, the physics that dictates how the decoupling happens is just standard model, weak interaction, that's all. And so we can actually compute the properties of this unibue very, very well. Okay? We know it's a thermal spectrum, and we know that there are 0.1% distortions coming from the decoupling process. And the energy density in this neutrino at early times is usually quantified as a ratio to the CMB energy density. So why it is effective number of neutrino parameter and effective. So this is a funny definition and has been chosen in such a way that the leading order number for n effective in the standard model is 3 for 3 families of neutrinos. And you see here also that there are some percent level corrections coming from various things like the QED equation of state in the early universe, finite temperature effects, flavor oscillations, transport, etc. And there's been a lot of effort in the last few years to really try to pin down this number to per mil accuracy. Now, the late time energy density of this neutrino background is normally presented, usually quoted in terms of this reduced energy density parameter omega nu. And omega nu, as you can see here, depends on the neutrino mass. And we don't really know what omega nu is, but only because we don't know what a neutrino mass is. But otherwise, this number here, 93.75 in the denominator, we can calculate that very well. Now, from the observational side, let's look at what we can do observationally when it comes to constraining these parameters. So n effective, for example. So the n effective parameter is basically characterizes the energy density contained in the neutrino background. So during early times when radiation dominates and the neutrinos were relativistic, you can expect n effective to have an effect on the universal expansion rate, particularly at BBN times, which is minutes after the Big Bang, and also at CMB times, which is about 400,000 years after the Big Bang. And so you can expect to see n effective showing up in a CMB anisotropies, which is usually depicted in a picture like that. It shows up in the diffusion damping tail. And for effect on nucleosynthesis, primarily the most affected element abundance is helium-4. Okay, and as you can see here in the list of numbers that I am showing you, the N effective value that is inferred from CMB and BBN are broadly consistent with the standard model prediction, okay, of 3. Now, less discussed is this idea of early free streaming. Now, recall that when we form this neutrino background, these neutrinos decouple from the cosmic plasma and then they free stream to infinity. Okay? By free streaming, we mean that the neutrinos don't interact with anything else again. And this free streaming is actually very interesting for cosmology because they actually end up affecting the perturbations in the space-time fabric, which is then felt by the CMB. Okay? So you can actually use the CMB temperature and polarization fluctuations to try to see if you can detect this neutrino free streaming. Okay? And indeed, if you do the calculations, what happens with the neutrino free streaming is that it causes a small phase shift in the acoustic peaks. So you can actually go and look for it. And many people have done it. This is an analysis from last year. And what they found is that a phase shift that is consistent with standard model predictions has been detected at 10 sigmas if you use just the Planck CMB data. And that significance goes up to 14 sigma if you include also data from SPT and ACT. Okay? And this is interesting because if you're interested in BSM physics in the neutrino sector, you can actually use this detection of free streaming to try to constrain, put bounds on non-standard interactions. Okay, we won't talk about it now, but anyone interested, there are some extra slides that I can show. Now, but probably what everyone thinks about when we talk about neutrinos and cosmology is what has become known as measuring neutrino masses with precision cosmology. And the idea here is that at late times, when the neutrinos become non-relativistic, they can be a dark matter. But still, because they have been free streaming for so long, they cluster very inefficiently on small length scales. So as you can see here in this little video I'm showing you, you have basically 2 universes that have different mixtures of cold dark matter and neutrinos. So on the left here, this is a cold dark matter only universe. On the right here, you have a universe that contains both cold dark matter and some massive neutrino hot dark matter. Okay? And you can see that even though the 2 universes have exactly the same initial conditions, over time, the massive neutrinos and the free streaming that they perform would eventually dynamically drive the distribution of matter into this form where on the right you see very little structure on small scales. Okay? If you squint your eyes, they look kind of the same, but if you look closely, they don't. Okay? So now simulations look good. If we want to do science, of course, you have to quantify it somehow, and the quantification is usually the power spectrum, okay? Which you can see here that the green line is substantially higher. That's the one with no neutrinos, but here the blue line, you replace some cold dark matter with massive neutrinos, and then you see a suppression, okay? And this suppression basically depends on the reduced energy density parameter for the neutrinos. Okay, who can measure it? Tons of people can, and here's a plot I lifted from the Planck paper 2020. It's a bit busy, so this is my own version of the same plot, which basically shows you the classes of probes that are sensitive to this power spectrum. Okay. Now, I've highlighted this red region, and maybe it's a bit early, but I'll come back to this point later on. This region here is only probed by the CMB primary anisotropies, and it's interesting because this region over here is actually the part that is probing directly the primordial fluctuation power spectrum from inflation. Okay. So anyway, we'll come back to this in a bit. Now, before I go on to talk about the bands themselves, let me also point out that there are also other low redshift probes that are used in cosmological neutrino mass bound derivations. And even though they are not actually directly sensitive to the neutrino mass themselves. So if you look closely here in the matter power spectrum, there are tiny wiggles over there, and these wiggles, if you go to real space, will turn into a peak. This is the baryon acoustic oscillations peak. And it's a very, very particular feature in real space, which you can then use to, if you detect it in your galaxy clustering surveys or whatever, then you can use it to construct basically a distance versus redshift ladder. Okay, and this is extremely useful because it's a very powerful probe of the low redshift expansion history of the universe, and hence things like spatial geometry, matter density, etc. Okay, so now let's look at the neutrino mass bound, right, from cosmology. So a lot of you probably would have heard about the CMB plus Stacy BAO neutrino mass bound that is extremely tight. And at the moment, this is that I took from the DR2 paper from DESI from last year. And you can see here the constraint, the 95% confidence constraint on the neutrino mass sum is 0.064 to 0.077, depending on which Planck likelihood you use. This comes from a lambda CDM plus neutrino mass sum 7-parameter fit. And if you just look at these numbers over here at face value, what you find is that they are about a factor of 20 better than what you can do from tritium beta decay, which is kind of crazy. What's more, this is the official party line, if you like, but if you dig into the literature, you'll also find that a number of people have been writing papers where they produce extremely aggressive bonds that even fall below the minimum neutrino mass sum or 0.06 electron volt established from neutrino oscillations. And what's more, the likelihood appears to peak in the region of negative neutrino mass. Okay? And this is seen in both Bayesian and frequentist analyses. So what I want to do is to basically say a few words about where this bound comes from. Okay, so to understand this bound, the first thing I want to highlight is who is actually driving the sensitivity to the neutrino mass sum. So first of all, I mentioned it before, but I'll say it again. The bound is from a basic lambda CDM plus neutrino mass sum 7-parameter fit. And the actual sensitivity to neutrino mass actually comes from CMB lensing, okay, which is depicted here in this green blob. Okay, so this is the degeneracy direction in the neutrino mass sum and the matter density plane. The green blob here comes from lensing. Okay, now there are two places where you can see the lensing signal. The first is in the TT power spectrum, where it manifests itself as a kind of smearing of the power spectrum. Or if you really like to do it, what you can do also is to try to reconstruct the lensing, the matter density along the line of sight that is causing the gravitational lensing in the first place, the small deflection in the path of the photons, okay? And that's called the lensing power spectrum, which is shown in this plot over here. And this green region actually comes from the lensing potential reconstructed from the Planck and the X data. And what you see here, is that there's definitely some degeneracy between between neutrino mass sum and the matter density. But the lensing potential is obviously not the only way in which you can use the CMB. The CMB itself contains a lot more information. So if you use the full CMB information, the bound actually is this blue area. And in fact, you can do a global CMB-only bound, and by combining the Planck data, the ACT data, and SPT data, and what they found here when they did that is a bound of 0.19 electron volt, okay, which is already pretty good. Now, what the BAO does essentially is to add this pink region. Okay, so I mentioned earlier the BAO doesn't actually measure the neutrino mass. It's not really that sensitive. And primarily what it does is to put constraints on things like omega m if you're looking at lambda CDM. Okay, so that's this plot over here. And as you can see, you have the pink region intersecting with the green region, and that's basically how you get a really tight bound, okay, on the neutrino mass. So in this slide, we can try to see where the negative neutrino mass comes from. So there are actually essentially two anomalies that you can trace negative neutrino mass to. The first one is the CMB lensing anomaly. And it's a long-standing 1 sigma excess gravitational lensing relative to lambda CDM prediction that has been seen in the Planck data since whenever. Okay? No one paid attention to it, not much anyway, because it's only 1 sigma. But if you think about it, you have a lensing excess, then, well, I told you before, if you have neutrino mass, the neutrino mass suppresses the power spectrum, right? But now we're talking about an excess of power from lensing. So you can sort of think about it in your head as if you have an enhancement due to flipping the neutrino mass to a negative value. Okay? So this whole negative neutrino mass business is really just a phenomenological description of suppression for positive mass versus enhancement for negative mass. Okay? Now, that's one place where you have a slight anomaly. Well, as you heard yesterday, it turns out that there is another mismatch, tension in the cosmological data between the CMB and the DESI-BAO results. And one way to phrase it is that the omega m that is preferred by DESI is lower than that preferred by the CMB. It's about 2 to 3 sigma mismatch or so. And this is bad news for the neutrino, because if you have less matter, that also means less lensing. Okay? So what it means is that this mismatch in the omega m essentially exacerbates the CMA anomaly to 2 to 3 sigma. Okay? That's the reason why it is that people have been finding a preference for negative neutrino mass. It's purely some phenomenological description. So you've seen this plot already. That shows the mismatch. What drives the mismatch, again, you've seen this plot, is essentially, some people have noticed it's the data and the BAO around the set of 0.7 bin around here, which is kind of driving the fit of the BAO data, which is the blue line, down here, whereas the CMB fit is the flat line. Now, if you're adventurous, you can, of course, also try to introduce a dynamical dark energy in the form of a modification to the equation of state. You give it a redshift dependence, and this is usually called a Chevalier-Pulaski-Linda parameterization. It's not particularly physical, but it does the job. But anyway, you have two free parameters, and you do the fit again. What you see is that you get a pretty good fit, okay, to the data. Interestingly, you can do the same fit to the supernova data, supernova 1A data, and you find also that this fits the supernova data quite well as well. So this has led to some discussions about whether the data is seeing a 3 to 4 sigma preference for dynamical dark energy. Now, in terms of what this can do for the neutrino mass band, well, essentially, by introducing 2 extra parameters and therefore bringing the preference of the matter density back to something that's more acceptable, you relax the neutrino mass bound. Okay? As you can see here, you're seeing a relaxation of a factor of 2 point something, almost 3. Okay, so you can compare these numbers directly. The second number here includes also supernova data. Now, W0, WA, that's one game you can play. We don't need to stop there. We can keep going and make our cosmological model ever more complicated. And that's what these guys did in the paper that came out about a month ago. And what they did is to explore what would happen to the neutrino mass band if you keep making your cosmological ever more complicated by introducing running, primordial tensor, spatial curvature, etc. Okay, never mind whether they're motivated or not, but you can play this game. And if you do that, what you find is that, there's a range of values all the way up to about 0.18 electron volt for the mass band. Okay? Now, last but not, there are other ways to get around this mismatch as well. You can directly tweak omega m by making the dark matter decay, for example, or you can make the neutrinos decay. Lots of games you can play. But of course, we can't rule out the fact that maybe someone didn't completely figure out their systematics. I don't know. I can't say. And there's even a more mundane explanation. Maybe the universe that we're mapping just happens to be a 2 sigma outlier. And that's something that we can't really exactly rule out. Okay, I'm going to skip this one. But anyway, what lies ahead? Well, there are these probes that are either producing data, like DESI or Euclid's been launched. There are CMB surveys as well. And I'm running out of time, so I will just leave you here with my summary, and thank you for your attention.
Thank you, Yvonne, for this great talk. So we have time for questions. There.
And thank you for this wonderful talk. 2 independent but maybe related questions. What do you think are the prospects for directly tackling the CNB?
The CNUB, yeah.
CNUB, yeah, so Ptolemy and things like that. And the second question is there any hope of using cosmology to differentiate between Dirac and Majorana neutrinos?
Okay, so I'll answer the second one first. Not really, I would say. I mean, circumstantial evidence maybe. So if you have a model, set prime, whatever, and it creates a delta N effective, and which are the right-handed Dirac neutrinos maybe, you can probably say circumstantial evidence that you have a delta N effective. But in a completely model-independent way, I would say no. Because like if you just look at the neutrino background, they're produced via the decoupling from just weak interactions. And the weak interactions doesn't care whether you're Dirac or Majorana. So yeah. Second question, Ptolemy. Well, The problem there, as I understand, is that there are quantum limits limiting what you can do. So one of the things that you really need to do to do this direct detection with the beta decay endpoint spectrum is that you need a very excellent energy resolution. And so they have this idea about basically embedding the tritium atoms on the on a lattice. But the thing is that once you do that, Heisenberg's uncertainty principle kicks in, and if you know where your tritium atoms are, then you can't really determine the momentum very well. So I don't know that it is that direct detection is foreseeable in the near future. That's what I would say. Yeah.
One more here.
Yeah. Oh, hi. Thank you for a nice talk.
Oh. There. Okay, sorry.
Yeah, hi. So in that simulation that you showed on page 13, yeah.
Page 13. Oop. Yeah.
Yeah, that's for dark matter and neutrinos, but they don't interact, right?
No,
So
they don't. No.
Yeah, so if they were maybe other than gravitationally, attractive interaction, then maybe the simulation would be more similar. I remember you had something about, you had some slides about beyond standard Moore scenarios where dark matter interacts with neutrinos. Maybe you can comment on that.
Okay, so these scenarios, there are dark matter neutrino interaction scenarios and bounds that people have put on this sort of interaction. And primarily what happens, and they have some very tight bounds, and the reason is that if you couple the dark matter to the neutrinos, you actually end up making the dark matter cluster less efficiently. So it's not the other way around. You don't actually improve the situation by coupling the two things. Yeah, and then the reason, simply because at early times the neutrinos are so relativistic, they tend to basically pull all your dark matter out of the potential wells. So the clustering is actually even worse. At late times, so you have an idea that you want to keep them interacting, or at late times, maybe? Maybe this is actually for discussion later on, but yeah, look for me. Yeah. Yeah.
Okay, just one more question, João.
Thank you for the very nice talk. Yeah, I was wondering about you mentioned that we can sort of measure the sum of the mass of neutrinos, but we need the prior from CMB.
Oh, that's the slide I skipped. Yes, I can show that.
Yeah, can we measure the sum of the mass of neutrino without in an independent way of the CMB?
Yeah, so good that you're asking because I skipped this slide. Unfortunately, you can't, and that's the point that I was making about the primary CMB probing this part of the power spectrum. That the CMB is the only way you can probe this part of the power spectrum at the moment, and which is the reason why it is that if you want to do an independent bound on a neutrino mass without using the CMB, you still have to use a prior, okay, just to anchor this part of the power spectrum down. Okay. Now, okay, you can envisage a time when we have Hubble volume mapping with 21 centimeters, let's say. Maybe when we get there, we can have like a completely CMB independent bound, but at the moment, we have to put priors just to anchor this part of the power spectrum.
Okay, so let's thank Yvonne again.
Morning. So our next speaker is Ettore Segreto, and he will talk about new developments in detector technologies, including quantum sensing. Okay.
Good morning. Morning. Okay. Good morning. It's a real pleasure to be here in Natal, thanks to the organizer. I was asked to give a review about new development in the detector technologies, and I think it is a really great moment to give this kind of talk, since our colleagues in LHC are building right now the upgrades for the luminosity, and there are a wave of new technology in the field of neutrino physics, astroparticle physics, and dark matter direct detection. So I will give a brief walk inside a field that is not mine, that is the upgrades of the LHC experiment, and then I will go to review some of the most promising technology which are emerging and that will tell us where the community is going. So this is really an impressive, one of the most impressive upgrades of the LHC luminosity, that is the inner barrel of the ALICE tracker. The key enabler of this technology is the stitching of photographic reticles that allow to build large monolithic wafer scale sensor that can be curved in a 65 nanometer CMOS process, and that allow to build band sensor, as I said. And the three layers allows to are built with two sensors, and the signal distribution and the power are on chip, and this has tremendous consequences about the material budget and power dissipation. In fact, these objects are cooled in air instead of water, and the pitch is also reduced. Going to Atlas, another impressive upgrade. Here the driver is the enormous amount of expected pile-ups, as you well know, and in this simulated event there are at least 88 regostatic vertex with 2,000 particles. This poses incredible, impressive requirement about the inner tracker. That need to have a high granularity, improved radiation hardness, and so on. So the collaboration decided to replace the inner tracker with a pixel layer close to interaction point and microstrips at larger radius with an impressive amount of silicon with about 180 square meters and 5 billion channels. So this is an impressive upgrade. The concept, as we will see several times along this talk, is that the technology is matched to the amount of radiation that the sensor needs to suffer. And so there are 3D sensors in the inner layer, while planar sensors in the outer layer. Atlas decided to use also a timing layer in the front, in the forward region that delivers 30 picoseconds resolution in time per track. This is going to CMS. This is a very elegant solution to solve a similar problem, that is the impossibility of read out the entire detector in at 40 megahertz. And it is the concept of the outer tracker, the PT modus, where two sensors are back to back, read out by the same ASIC that can make correlation between the time the crossing time of the particles and the position, So particles with large transverse momentum have almost close hits, while particles with small transverse momentum that are less interesting fall outside the windows of interest. This kind of technology allows to perform for the first time a tracking trigger at level L1. So it's really an elegant solution. Probably the most impressive for an external eye of the entire upgrade is the end cap calorimeter of the CMS, which has an extremely high granularity, is a sampling calorimeter. And again, we see the concept of having full silicon detector in the region of light fluence that is mainly in the electromagnetic region and part of the hadronic one. and silicon PMM tiles in the regions with low fluence. This is a really 5D calorimeter, since it reconstructs the three spatial coordinates, the time and the energy. And this gives a powerful hand for rejecting pileups. And also it is an ideal test bed for new reconstruction technology, for example, based on graph neural networks. The LHCb will go through an upgrade more later in the future, but the concept is always the same. The need coping with an extremely high pileup rate requires adding the fourth coordinate to the reconstruction of the particle, and so the time becomes the four coordinates with the resolution on the level of 50 picosecond per inch. Let me switch briefly to a new concept, since these upgrades are very important by themselves, but also represent a test bed for future ideas. We have seen in this conference two possible future calorimeters for future colliders, like the CLD, where the extreme granularity of the detector is exploited with an electromagnetic part made by tungsten silicon, the silicon with the silicon cells 5 by 5 square millimeter, and a hadronic part made of scintillating tiles. A very intriguing idea is the one proposed by the idea working group, where the electromagnetic calorimeter is made of crystals, while the followed by an hadronic calorimeter. The interesting thing is that here is proposed the dual readout of the signals, that is the simultaneous readout of Cherenkov and scintillation radiation, since this gives the opportunity to reduce significantly the uncertainty about the energy measurement, the calorimetric measurement of hadronic showers. That depends significantly from the fraction of electromagnetic component. Since Cherenkov radiation is mainly sensible to the electromagnetic component, this is a convenient way to measure this fraction event by event. This concept of detection allows me to make a big jump and to switch to neutrino physics. This is a very important year for neutrinos, 70th year for the first discovery of neutrinos in 1956 by Ryan and Cohen, because the idea of detecting simultaneously Cherenkov and scintillation radiation is also being put forward by neutrino experiment, for example, by the TEIA and this demonstrator EOS, that has been already mentioned by the previous speaker, because this allows to preserve the advantages of having a directional detection of Cherenkov of neutrinos with Cherenkov radiation together with the calorimetric reconstruction of scintillation light. This is possible because a few enabling technologies that you see listed here, that is the development of new targets.
I'm going to use this. The sound is not getting at the end.
Okay.
It's just to take this. Oh, sorry. Sorry for that.
Hello? Okay. It's better. So the idea here is to preserve the advantage of detecting Cherenkov light with the directionality and the calorimetric measurement with scintillation. So you can separate Cherenkov from scintillation by timing, since Cherenkov is much faster than scintillation, by wavelength, given the broad spectrum of Cherenkov light, or by the angular distribution. So a few enabling technologies have been developed that will allow to make this kind of separation for future detectors. So the development of new targets, this water-based liquid scintillator, a very fast, large photosensor, LPPD, that I will talk briefly in a few minutes, and the chroicons that allow for chromatic sampling of the photons according to their wavelength. LAPPD are very intriguing new generation photodetector, large area picosecond photo device with a very large area at the level of 20 by 20 square centimeter in this case, with two-stage multiplication given by microchannel plate and segmented anodes. This allowed to reach performance of this level with the quantum efficiency of a photomultipliers, more or less, from 20%. Time resolution better than 100 picoseconds, and space resolution better than 1 millimeter. Very negligible dark counts. Dichroicons is another intriguing concept that is essentially a Wilson cone made by dichroic filters. Dichroic filters are optical devices that allow that have optical filters that have high transmission below a certain cutoff, and reflective above the same cutoff. So this allows to sort photons according to their wavelength. And for example, long wavelength photons pass through the dichroic filter and the detector by one of the sensors, and the Cherenkov light is detected by the other sensor. This has been proven to be effective, and the step forward is full coverage of the surface of a detector with an hexagonal light concentrator, one with the correct filter for Cherenkov, one for scintillation light, that then are alternated. This is very difficult to see. That allows to separate efficiently all the light that arrives on the photosensor. So this is a simulated event where you can see the Cherenkov and the scintillation light separated. On this line, there is a recent R&D that plans to use the Arapuca technology, of which I will talk in a few seconds, to separate Cherenkov Barclay from scintillation. The project is at an early stage of R&D, but is very promising. The Arapuca is a photon detector that has been developed in the framework of the Dune experiment. Arapuca is a word in the language of native Brazilian that means traps for birds. In this case, we want to trap photon inside the bird in order to increase the active, the effective surface of the silicon PM that detected the light. It is a reflective box. The acceptance windows is a dichroic filter with the Weber shifter and a light guide in the middle. So the photons are trapped through a double shift of the light, trapped partially by the reflection on the dichroic filter, partially by the light guide, and the fraction of them are detected by the silicon PM. As I said, this represented the baseline design for the Dune experiment. Dune, as you have already heard, is building the far detector in South Dakota. There are two slightly different versions of the far detector, the horizontal drift and the vertical drift, depending on the direction of drift of the electrons in the time projection chambers. And there are also two different flavors ex-Arapuca in the two modules. For the horizontal drift, they are bar-shaped devices with dimension of 200 by 10 square centimeter. And in the vertical drift, they are big square. The good thing is that this device have efficiency around 4–5%. That is quite a lot for this large surface. And this, for example, this bar corresponds to 5 or 6 8-inch old-style photomultipliers. The X-Arapuca are being, for the horizontal drift module, are being assembled in Brazil between Unicamp and Senepen, that hosts the Sirius laboratory in Campinas. And most of the mechanical components and the opticals are produced by Brazilian companies. We built the first two modules, so we are missing 1,498. We will take a couple of years to complete them, but we are on the way. Another interesting concept which comes from liquid argon, mutated possibly from collider physics, is the pixelated readout of TPC. This is realized in the near detector of the experiment that is a key element to reduce the systematic neutrino oscillation measurement. It is a segmented detector with a very small drift, 50 centimeters, and designed in this way to cope with the high pile-up rate. Also in our experiment, there will be an high pile-up rate in the near detector up to about 100 in interaction per speed, and the readout is pixelated. Instead of traditional wires, this allows to perform a native three-dimensional reconstruction of the events and to reduce significantly the problems in the eventual problem in the reconstruction due to ambiguities. Let me jump now to a concept that has been developed in the recent year by the Large Neutrino Observatory that started with the KM3 net experiment and then been adopted also by the other, by the ICHEP ICHEP SWGO, that is the multi-PMT concept. This is very, again, another smart idea. That is, in the case of KM3net, is an arrangement of 31 photomultipliers inside the glass sphere. So there is a 4 pi angle of view and very high efficiency, and the system is highly efficient in discarding the background of potassium-40 and bioluminescence, since this device goes deep underground through internal coincidences inside the same sphere, and is clearly much more resistant to single PMT failures. Similar concepts have been adopted by ICHEP, as you have heard during this conference, with 19 photomultipliers and a 26 centimeter vessel by IceCube, with 2 different flavors of multi-PMT concept, one with 24 photomultipliers, one with 2 back-to-back photomultipliers with the 8-inch acceptance window. And the Triton Observatory, which enriched this sphere with the silicon PM rise in the dead region to improve the timing. Now, let me go from a large experiment to a small one to very small threshold. As we have heard from the previous speaker, coherent neutrino nuclear scattering is a very hot topic nowadays, and was observed by the coherent collaboration in 2017 as important implication for beyond standard model physics, for monitoring nuclear plants, also for dark detection. There are several experimental efforts going on for the detection of this CNNS. I want to put the highlight on our local effort, that is the CONI, that is installed at Angra 2 reactor, that uses the technology of skipper CCD, that are CCD that are able to sample the same charge multiple times in a way that is possible to reduce substantially the statistical fluctuation in the charge detection up to arrive at the single electron resolution. So if you go passing multiple times your charge, you clean significantly your event. While coherent nucleus neutrino scattering is the subject of this experiment, it represents a reducible background for dark matter experiment. In this field also we have seen a tremendous amount of innovation. I want to cite just one. Many of these experiments switched from standard photomultipliers to silicon PM. A notable example is the dark side that developed an extremely large tile of silicon PM that was difficult to think a few years ago, with an area of 20 by 20 square centimeter, with an extremely high detection efficiency, close to 20%. operating in cryogenic condition with low radioactivity background. So it is an extremely attractive object for future developments. In the field of silicon PM, it's worth mentioning also what's coming next. So the digital silicon PM are becoming reality. This is possibly the perfect photodetector of the future, where each pixel is connected with its own electronics, so that you get one timestamp for each pixel that tells you when the photon when the photon hit the pixel. Another interesting development is the one of back-illuminated silicon PM. What is limiting the sensitivity of silicon PM is the filling factor and the reflection of the photons on the surface of the silicon PM itself. In this case, silicon PM are illuminated on the back, where this problem is solved, and the reflection limited by anti-reflection and texturing of the surface. Just to conclude, a couple of very futuristic detector, the Liquido, that is breaking the paradigm of scintillation detector, of very clean and transparent scintillation detector with opaque medium, so the light is confined to Rayleigh and misscattering, and so you get three-dimensional reconstruction through an array of fiber and silicon PM, and we have been presenting in this conference the cube and the tile prototype. Another example is the Platon, that is a combination of human eye and fly eye, and is taken from the photography. And the idea is to take a picture of an event from different angle view, so that you can reconstruct very fast three-dimensionally any kind of interaction inside the active volume. Just to finish, 1 minute, few seconds, the quantum dot is a field that is taking a new life in the last year, because they allow you to tune the emission of the light according to the dimension, to the doping of the quantum dots, that allow to build very compact photon tracker, for example, by growing quantum dot in a matrix of gallium arsenide. Last but not least, that's something that is of interest of the entire community, is the possibility of engineering the Stokes shift of quantum dots with using different material, where the nucleus is the emitter and the outside is the absorbers. So you can have two different, very separate bands for the absorption, for the emission of the light, and this allows to build, for example, light guide with the propagation length that is extremely big. So these are my conclusions. I leave it to, and that's it.
Thanks, Ettore. We have time for one question.
Thank you very much for the talk. A question regarding the dichroicons. You've shown the picture with 2 sets of photosensors. Has anyone tried to do more than 2 at a time? So red sensitive down to very low wavelengths?
Sorry, which?
Slide 12, I think.
Okay.
Yeah, here. So there's red sensitive and blue sensitive. Has anyone tried to put many types of photosensors in such an architecture?
Well, as far as I know, this is, but this is a field that is rapidly growing, so it's an R&D phase. As you see, also this other geometry is very intriguing, so new ideas are clearly welcome, but I'm not aware of people using more layers of the correct filters. In principle, you can do it. It pays something in the Cherenkov-2 scintillation separation.
Thank you.
Okay, thanks. Let's thank our speaker again. Obrigada, Ettore. Funcionou com o microfone. Já está comigo. Okay, our next speaker is Alberto José Roque, and he'll talk about technological spin-offs and industrial applications.
Thank you for being able, as a condensed matter physicist, I think I never dreamt to be giving a talk at ICHEP. So it's quite an honor to be here. And I'll talk about CNPEM and how this is connected to let's say, everything that has been discussed here. We are at Campinas in the state of São Paulo. So the conference is way up north, and we are very close by to Unicamp, but we're not really connected formally to Unicamp. We are similar, for those who know, similar maybe to PSI in Switzerland, and maybe we have some similarity to some of the national labs in the United States. We are the home of the only synchrotron light source in Latin America, but we have very diverse activities, not only synchrotron science, of course, but also biorenewables, biosciences, nanotechnology, and mostly engineering instrumentation. That's what I will focus here. We are a private non-profit organization that signs a contract with the Ministry of Science and Technology and Innovation, and we also have the partnership of the Ministry of Education and Ministry of Health, and we're very much a mission-oriented institution. We have about like 1,300 employees, and if we count postdocs, students, trainees, and outsourced personnel, it's a campus of a bit more than 2,000 people, let's say, every day over there. We also have a faculty, a recent addition to CNPEM. It has one course for 40 students only a year, so it's a bachelor's in science, focusing mostly on multidisciplinary education and project-oriented. And since the very beginning, they actually, let's say, come to the CNPEM to be acquainted with very sophisticated experimental techniques. It's a very competitive, it's sort of 60-1, so today in Brazil, I think is regarding science classes or science undergrads, is probably the most competitive one these days. And we also have a very major project, which is building BSL-4, the first BSL-4 in the world that will be connected to a synchrotron light source, but it's not only BSL-4, it's also, we're talking about pathogens. For those who don't know, you classify pathogens, the danger of pathogens from 1 to 4, and if you want to work with Ebola, you need this BSL-4, and we're going to connect with 3 beam lines of a synchrotron light source. So it's quite a challenging and will be very important for such an important, we all passed through the COVID pandemic. The origin of the lab was more than 40 years ago, actually started at CBPF as an idea, as the physics community sort of got organized to build a large infrastructure, and a synchrotron light source was chosen. So now I have to compete with the brain, yes? Hopefully you are listening, hearing me. So it was a very important point, in my opinion, to the Brazilian science, because it was the very first big facility that was decided to actually be built in Brazil. So this was very important for the training of human resources. This is the most important thing to be able to reach where we are today. And around 85% was built in-house, not only in Brazil, but in-house. Not only the design, but the construction of the magnets, vacuum systems, power supplies, all built in-house. But it was not a competitive machine at the international level. It was a second-generation light source, and the world was already at the third-generation light source. That's when I went to CNPEM to actually build a new light source in Brazil. Initially, it was planned to be a third-generation light source, similar to Diamond, Soleil, etc. But MAX4 was being built in Sweden, and we have decided that we had the capability to actually build a similar machine. So there was no machine operating back then that is called fourth generation, and was a successful story, and it has been operating since first beam was end of 2019, and we've been operating successfully. So now I'll focus from this how we actually are collaborating with Brazilian industry. So since the very beginning, we understood the importance of connecting to the Brazilian industry for a project like Sirius. It's an expensive project for the country, and it was clear that science, of course, that will come out of it is very important, but it's equally important to actually engage Brazilian companies. And we did many, because we are private institution, we have a lot of flexibility on way we actually make the contracts with the companies, and we actually developed dozens of different kinds of interactions. I'll show a few examples. And we have today in Brazil, when we started, we had no Brazilian company that had sold components to accelerators, and now we have more than 40 companies that are selling components to us every day. So it was quite successful. More than 80% was actually spent in Brazil. So this was very important for the project. And you can visit, we have a stand here, 4 of the Brazilian companies, Engecer, that did ceramic vacuum chambers, FCA Brazil also connected to vacuum chambers, Pytech, and VEG I'll talk about. One was connected to detector development, VEG to the magnets. So we can see here, and you can go outside to talk to them. So I'll take few examples then. Detectors. So we understood this could be a very important development in the country. So if we had the capability of dominating the detector technology for X-rays, we actually could develop things that are customized. I'll give an example for the Orion project. So we joined the consortium, the MedPix consortium at CERN. So we always have been very close to CERN since the very, very beginning of the lab. A lot of people said it would be impossible to actually develop this in Brazil, but today we have a company, a Pi Mega company, that is selling to synchrotrons abroad. So it's quite a successful case. And now we have the challenge of Orion. Orion is this BSL-4 lab connected to synchrotron light source, and there will be 3 beam lines. All of them will do, let's say, tomographic imaging from cells to small animal models. And we're going to have a very high throughput, let's say, of data to generate this tomographic imaging. So we're developing a new detector now based on time peaks, also from CERN. And then we're going to actually need to process this very large amount of data and transfer this to the server. And then we have Marco Leite from University of São Paulo that is connected to Atlas. And he has been doing some experiments at Sirius for the development. And then we thought, well, why not actually develop Brazilian companies to actually be able to produce Felix in the country? And we are supporting this with our own budget because this is fundamental for the 2P detector. So this is an example of how something connected to synchrotron science can actually be connected to a development supporting of the community here, the high energy community. A second example, connected to the previous talk, is the assembly of the Arapuca detector. So Ettore described this in great detail. And we are supporting, because he's at Unicamp, and there is difficult to actually do large-scale assembly of all the detectors. So we have a partnership now supporting also the community. Most of the detectors are actually being assembled over there, showing once again that CNPEM can be a hub to actually support the community. Now let's move to another successful case, an extremely interesting case in my opinion, and that could be very important for the future collaborations with CERN, impacting the high energy physics community here in Brazil, maybe also abroad. So we had to produce all these magnets, and we actually could buy them from abroad. Max 4 bought them in Europe, but we wanted to actually develop this capability in Brazil. And we have absolutely no Brazilian company actually dedicated to magnets, and it would be very difficult to start from scratch a company that would be able to actually produce at the scale that we needed. So we looked at the, let's say, closest thing to a magnet. WEG is the biggest seller of electric motors. And we thought, well, this is not so different maybe to a magnet for an accelerator. It took a while to actually convince them to engage in this development, but eventually they did accept the challenge. It was more than 4-year development. And at the end, they produced more than 1,000 magnets. I would risk to say some of the best magnets in the world, and that today could be produced very quickly because there is no machining. Everything actually is a laminated magnet that was assembled with an extremely high precision, and you can actually visit one of the quadruples at the stand here. So it was really a cool development. It was not that we simply had a bid and they would produce, because they didn't have, in fact, the knowledge to actually produce a magnet. So it was a co-development. We did the design. We did together prototyping. They did a pilot batch. Then, once approved, they would do the eventually serial batch and the production of all the magnets. And now, also connected to the magnets, you need the whole support to have the challenge of having very high, let's say, the first mode, natural mode of oscillation had to be very high to decrease the probability of instabilities in the machine. I think this is one of the highest that we have in the world, and this involved a lot of other Brazilian companies besides WEG. So we have today, let's say, a chain of companies that we can produce the whole girder system. And then comes to CERN, and where does this connect us? Brazil today is an associate member, but even before that, during the COVID, we signed an agreement with CERN because we needed to actually increase the interaction. And one of the most important things of this interaction is the capability of quickly transfer technology, quick learn, because learning is the most important thing. And we were, as the director at some point of Fermilab said when he came to visit CNPq, is a warm lab. And we needed to, in my opinion, for the future to become more colder. So we wanted to actually learn to develop a device, a superconducting device. This wavelength shifter actually was chosen. And we have acquired all the capabilities, complete capabilities, and we have finished this. And it will be installed at Sirius next semester, this semester, because now we're in August, this semester. And we'll be able to actually provide high energy X-rays because we're going to have a magnet of close to 7 Tesla. And also we wanted to get into the proton accelerator business, mostly at the beginning because of possible applications in health. And we also then discussed with CERN and learned to do this RFQ component for the beginning of the acceleration. We have reached already 1 MeV, and we're working with support of the Ministry of Health to eventually, in a couple of years, reach 10 MeV, all done also completely in-house. And from this was very important for the final decision of Brazil to actually become an associate member, because now when they had the argument that Brazilian companies could sell to an accelerator structure like CERN, we had actually a reality now. We had many Brazilian companies that now could have this capability. And we became an associate member state, Brazil, in 2024, and the ILO is actually connected to Sirius Rafael Navarro, so we're supporting all the activities. And this is very important because a lot of companies actually don't have the capabilities to actually discuss technical details about accelerators. So it's sort of a liaison. Not only have the ILO, we have a whole lab that can actually support and help the Brazilian companies actually sell to CERN. We have been helping to actually organize a lot of activities connected to this ILO. They are organizing this, let's say, catalog, virtual catalog of Brazilian companies. I think this will be very important. And we have managed to have 6 Brazilian companies already in this couple of years since the association to actually successfully get to the compliant bids, and eventually 2 won. So 2 out of 6. So I think we're just learning actually from the companies actually also how to actually participate on the bids. I'm very hopeful that this will increase quite a lot. So now my final part is the connection of CNPEM and the community to CERN's next big project that you know much better than myself. So FCC is the next big project, and there is a transfer line over there that is about 5 kilometers. Sirius is half a kilometer, so it's something 10 times bigger than Sirius. And we saw that the magnets that were developed for our booster could be, are very similar to the technical needs of this transfer line. So we sort of discussed and proposed that maybe we could produce these magnets. CERN thought this could be an interesting opportunity. And we are going to actually develop the prototype of these magnets, slightly changed from the original booster, Sirius booster magnets. And we are confident that WEG will also be engaged. So this means that we have a very successful story of developing a technology in Brazil, building a competitive machine, and developing a company that maybe now will participate in the largest, let's say, accelerator ever built by humanity. The second one that I hopefully will actually move forward is our involvement with LS3 magnets. It was discussed here, and the center magnet is being discussed that maybe could be produced in Brazil. I think this would be a major achievement. Imagine that when you go down and you see the Alice magnet open, the Alice detector open, of course, you could see maybe a magnet painted in red, in yellow and green, showing that Brazil has been able to produce. We are already working on, let's say, the specifications, and hopefully we'll sign something formally with CERN to actually produce these magnets, at least the first prototype. And this is, of course, involving Saclay as well, and CERN, and many, many different actors. That's it. Thank you very much.
Thank you. Do we have questions? This one here.
Well, thank you very much for the nice presentation. I'm here? Yes. Could you tell us how you collaborate with other Latin American countries?
Well, we have the collaboration as users. So we have traditionally around 10% of the users of the synchrotron light source coming from countries in Latin America. This was before Sirius, because now Sirius is competitive in a worldwide, let's say, way. So we're increasing the number of users from Europe, United States, and China. So now there's a strong competition, which I think might be healthy to the Latin America community. The next step, and I think now that Chile has joined CERN as an associate member state, we could actually engage maybe in joint projects for let's say, accelerators or something like this. We've been just starting the discussion with Chile, and I think that would be a very good movement. My dream is that in Latin America we'll organize ourselves to actually propose together more challenging competitive projects. And we are here to support.
Okay, thank you.
More questions? No? So let's thank our speaker again. Thank you.
Thank you.
We have lunchtime now when we convene back here at 2 p.m.